The FRQ we're going to talk about today falls into the QQT category. In this one, you've got a student, a mass, a 0.125 kilogram mass on a spring, and you set it into oscillation. And the student takes some data as shown by these two graphs, a position versus time graph and a velocity versus time graph. The question asks for you to make a graph of potential energy as a function of time. And make sure you label any intercepts, asymptotes, maxima, minima, etc. And then the second part of the question is to graph the acceleration as a function of time. Now the thing to keep in mind is that your potential energy, of course, will fluctuate from 0 to some maximum value. At equilibrium, all kinetic energy becomes, all the energy is in kinetic energy, and then as the object hits its maximum or minimum, all of that kinetic energy is converted into spring potential energy. Because you're given a graph of velocity versus time, you can use that to figure out something about the kinetic energy of the mass. Don't think that that graph of position versus time is going to help you, because that's nothing about the way that we can find a k value. It just shows amplitude as a function of time, but we don't have a k value, so it's not really going to help us do a 1/2 kx squared calculation directly. We're just simply finding the maximum kinetic energy. So the kinetic energy, of course, is 1/2 mv squared. So 1/2 the mass of 0.125, and then you have to find the velocity, that maximum velocity. On the graph, that max value was 1.6 meters per second squared. So using these numbers, you'll come up with 0.16 joules. So that is the maximum kinetic energy and also the maximum potential energy. So then the question becomes, what positions do these things happen at? So you got to keep in mind that at the maximum potential energy happens when you're at a high point. A high point happens when your velocity is 0. So looking at the velocity graph at 0 seconds, 0.5, 1.0, etc., is when the velocity is 0 and you would have maximum potential energy. So here we have the actual graph of the maximum value of 0.16 joules, and you find those maximums at 0 seconds, 0.5, 1.0, etc. And of course, when the velocity was a maximum is when your potential energy is a minimum, and that would be these points along the 0 mark. And then you use a sinusoidal function to connect all of the dots. So the key gives you some points. 1 for a reasonable sinusoidal shape, 1 for having the maximum on the graph labeled at the certain times, and then 1 point for having a maximum and minima with potential energy difference of about 0.16 joules. Part B asks about acceleration as a function of time, which of course is going to fluctuate as the force fluctuates, as the displacement fluctuates. So really it's about finding maximums again. And you can find that the maximum acceleration is equal to your maximum force over the mass. And you know the maximum force is your k value times your maximum x displacement over mass. Now you can find the maximum x displacement by looking at the graph, but it really comes back to that k value again. So how do you find k if you don't have the initial stretch we've done in other questions? Well, you know the period. You can use information about the period of this object, 2 pi square root of m over k, and then of course solve for k, do some algebra and find that k equals m times 4 pi squared all over t squared. So now you can put in, knowing what the period is, and you say, well, what's the period? You got to go back to your graph and say, all right, well, when does this position repeat? And you say, oh, it's every 1 second from beginning position to another identical position. So you have the period, you have the mass of 0.125 kilograms, and you can put everything in to solve for the K value. And so if you plug in your values, you'll find the K value was 4.93. So then we can go back up here and say that my maximum acceleration is my max force, which is K of 4.93 times my maximum displacement of the spring. Now that was 0.25 meters, and the mass is 0.125. Maximum displacement of the spring, that's amplitude. So again, looking back at that original graph, you can see the oscillations go from a 0.5 to a 1.0. That's all the way from here to here is 0.5. Remember, your amplitude is right in between there, so you end up with a 0.25 as your amplitude. And then when you solve, you'll find that the A max value is about 10. It's 9.86 meters per second for me, roughly 10. And then you can construct your graph here and find, okay, where does your maximum acceleration would happen when you have the maximum force. And you have the maximum force when the object is stretched the most. And so you end up with a graph with your maximums at 0. And of course, you can have a negative this time at the 0.5. So the same alternation of 0 to 0.5 to 1.0, but alternating between a positive and negative value. So point values, one for having a correctly labeled maximum of 10, one that's either a sine or cosine curve depending on where you started in relation to your original graphs, and one for a graph that has an appropriate phase relationship given position and velocity graphs. So keep in mind, phase relationship, that's shifting side to side. So you look at this velocity graph, and you see the velocity starts at a 0, but it's going towards the positive direction. Now that would mean that your object is getting faster in the positive direction. So you come back to your acceleration graph. You have positive acceleration, your maximum positive acceleration, and it starts decreasing as you pass through that location. The next question says, okay, let's talk about a new concept here. Let's say, what experimental procedure could that student use to collect the necessary data, including equipment, to answer the question? What the question was, what the student wanted to determine was whether the relationship between the restoring force by the rubber band and the amount it is stretched is that of an ideal spring. Hooke's law, F equals negative kx. There's a linear relationship there. So if you kind of have that equation in the back of your mind, like, well, I just want to prove that the graph, some sort of graph, would be linear. So in part C, you get 3 points. 1 for a reasonable experimental setup that would allow for actual measurements to be taken. 1 point for mentioning what you're going to measure, but no extraneous measurements. And 1 point for evidence that multiple trials are performed. So it's a pretty quick statement. Hook the rubber band over the horizontal rod, measure its length, hang an object of known mass from it, measure the new length. Then hang another mass, measure the new length. Then hang another mass, measure a new length. And if you keep doing that, you will end up with a way to gather the data that you need. Notice that part C just says what's the procedure and what data, not to analyze it. If you look at part D says, okay, now you've gathered this data, how should the student analyze the data to determine whether the relationship is truly linear? And what evidence from the analysis would be used to make this determination? So in part D, you'd plot, you'd make a graph, you'd plot the rubber band stretch as a function of mass. And a linear graph would show that the stretch and the force are directly proportional to each other as they are for an ideal spring. So part D had the last 3 points, where 1 point was earned for an appropriate analysis that would check for linear relationship between force and rubber band stretch. So is your method correct? Is it going to work? 1 point for indicating an appropriate characteristic from the analysis that signifies a linear relationship. So what is it that signifies it? And a point for indicating that a linear graph means f is proportional to x. as in the ideal spring.